Hello, ECCL channel greets you. Here is a converging lens. Thinner at the edges and thicker at the center. We say that the surface is convex. You can get the image of an object using a lens. It will form on the other side of the lens. We observe that it is overturned and that it is captured by a screen. When it does, it is said to be a real image. Not all optical systems offer a real image. The magnifying glass, even if it is a converging lens, in its normal use, offers us an image which is on the same side as the object and which is not on a screen. It's a virtual image. The same goes for the microscope, the astronomical telescope. The same goes for corrective lenses. But, in the case of the projector, the image of course forms onto a screen, it's real. With the camera, too, the image is formed on a sensor, it's real. For the smartphone, which has a camera, this is also the case, and for our eye, like a camera, it's the crystalline lens. Here, that is the converging lens and the image is formed on the retina. I isolated two rays, here, coming from B, a particular point of the object. Two rays among the infinity of rays since B emits in all directions. These two rays, at the exit of the lens, converge towards the same point B', which is the image of B. If the image is formed in front or behind the screen, we cannot see it. If the image is on the same side as the object, we can see it, but the eye will be placed on the right, here. The image is virtual. This is the case with the magnifying glass I was talking about, for example. I come back to the real image case. Here, I let this appear in order to explain, but what you see is what is being scattered by the screen, which is a scattering object. The information from B, here, does not arrive in the same place, and so, we see something blurry, since at that moment the image of a point is not a point. To get the sharpness, I can move the object around, that is called focusing. Move the lens, possibly the screen, or even, as is the case in our eye, make the curvature of the lens more or less convex. This is what the ciliary muscles in our eye do. We will see that in another video. They manage to modify this curvature. A little vocabulary. Here is the symbol of the lens. This particular point, which is the optical center, is the origin of the principal axis, which is an axis oriented in the direction of propagation of light, so in my example, to the right, and graduated according to a chosen scale. I also wanted to talk to you about the principal focus, or focal point, here, which is an important point because its position is characteristic of this lens. It is important. Its name, focus, means hearth, in Latin. If we form the image of the sun on a leaf, a tree leaf, a dry leaf or even a sheet of paper, we can start a combustion because all the rays here, and therefore all the energy they carry, will be concentrated at the same point. This allows me to speak here of the focal length between O and F'. It is a characteristic of the lens. It is here plus 125 mm, but this lens is only an example. It is an algebraic value. The focal length is OF'. How to draw the image of an object on a sheet. So I chose small squares here, and remember, there are three particular rays you must know. Any incident ray traveling parallel to the principal axis will refract through the lens and travel through the focal point, On the opposite side of the lens, a single ray is not enough to get a point. I need a second ray. The one passing through the center keep his direction. So I can get B' from this and already represent the image A' B'. To reassure myself, I can represent the ray which passes through the focal point F. It comes out parallel to the principal axis and I check that it also passes through B', so that I can build my image here. I remind you that the image and the screen must coincide to obtain sharpness. That's it for this video. Thank you. Hello, ECCL channel greets you. Two words here on the notion of magnification, gamma, which is the ratio of the size of the image to that of the object, in algebraic value. Here is an example here, where object AB and its image A'B' have the same size. So, I'm going to write that gamma as -1. In absolute value it is 1, since they have the same height. But as the image is reversed, I will have a negative magnification. Note that the magnification has no unit since it is the ratio of two magnitudes of the same kind. I will submit to you a second example, where the image is twice the size of the object. So, I write that gamma as 2 in absolute value, otherwise it is -2, -2. Again to mean that the image and the object are not oriented in the same way. I can show you a smaller image, because the image is not always bigger, it depends. And here, for example, the image is twice as small. So, I write that gamma, in this situation, is worth -1/2. The magnification is therefore not characteristic of the lens, since for the same lens, we obtain 3 different magnifications. Here's even a fourth, positive, when the image is virtual. This is the case with a magnifying glass, a microscope, a refracting telescope or corrective lenses. There is actually an infinity of magnifications. I would like to show you 2 triangles, here, that's why I left the particular ray which passes through the optical center which we know is not deviated. Which are the triangles OAB and OA'B'. So why am I showing you these 2 triangles? This is because they allow us, being homothetic, to write this relation in another way. Indeed, according to Thales' theorem, A'B' over AB equals OA' over OA equals OA' over OA. That is to say that the magnification is the ratio of the sizes. But it is also the ratio of the distances, from the lens to the image, over the distance from the lens to the object. An exercise, to illustrate all of this. You can stop the video if you want to do the exercise, otherwise I will continue. We have information on distances here, not on the sizes. so the object is 225 mm while the image of this object is 450 mm from a lens, which we don't know anything about yet. But we can answer the first question about magnification. So, precisely, thanks to the second part here of my relation, by making the ratio of the distances OA' by OA. So, I know that A' and A are not on the same side of the lens. We saw that in the constructions, and so I'm going to put the minus sign here and find that the magnification is -2. If I am given the object size, now I can find the image size by doing gamma times ab and I find -150 mm. If I am asked to find the position of the image focus f' by construction and to deduce the focal length from it, at that moment I take a sheet with small squares, a scale, here, which is suitable, that is to say 1 cm for 50 mm, and I can place the object AB, its image A'B' since I have everything I need. I can even represent them since I have the size of the object, and in question 2, I found the size of the image. So I can do this diagram. How to locate f'? Well, I know that the ray coming from B, parallel to the optical axis, will emerge passing through f'. Of course I extend it to B'. The point of intersection here is f', the secondary focal point. This is what I'm asked. This allows me to find the focal length here, which is therefore 150 mm, by construction. Contrary to magnification, the focal length characterizes the lens. Even though the magnification varies, the focal length remains the same. That's it for this video. Thank you. Hello, ECCL channel greets you. If the eye model is proposed in the chapters on converging lenses, it is because the crystalline lens is a convex one. It would be necessary to consider that both crystalline lens and cornea comprise the eye's optical system, and so to assimilate it to a single lens, of which I could represent here the symbol. I preferred to keep the drawing to explain how the ciliary muscle works. Look at the lens. When the ciliary muscle is working, it can just as easily make the lens more bulging, we say more convex, that is to say more convergent. The focal length will then be rather short. But the same ciliary muscle could work the other way around and stretch the lens to make it less convergent. And so, at that time, the focal length would be greater. So what is it for? Well, this serves to make the image sharp. That is to say, to position the image on the retina. The retina, which is a little our own sensor and which lines the bottom of the eyeball. This is called accommodation. It works a bit like in a camera. We want to make the foreground image sharp here. It forms behind the sensor, that is not the right setting. The foreground image will not be clear, so we will have to change something. Here, it's a little different from accommodation, we call that focusing. It is a question of moving the lens here to obtain a clear image on the sensor. The same goes for the background image, which is formed roughly at the level of the image focus. We talked about it when it was a question of evoking the image of the sun at this image focus. In the first video, focusing consists in placing, therefore, this image on the sensor, but by moving the lens on the principal axis, while the eye, to accommodate, will change the curvature of the lens. I have a scale problem here. You may have noticed it already. It is that if the eyeball that I represent here has a diameter of 2.5 centimeters, it is because the object which is there is less than 2 centimeters. So there is a problem. It's never neat. It's not possible. So this situation is paradoxical. But this problem of scale forces me to change the situation. So forgive me. It's a little smaller. But I have to if I want both at the same time. An object 20 centimeters from the eye, or a little more, and the model of this eye. So the image would be sharp if the eye could accommodate to place it on the retina, I said. But I wanted to talk to you about somewhat problematic situations. For some people, the eye is unable to accommodate. The myopic eye, for example, cannot always accommodate, especially for distant objects. When the object is very close, there is no problem, but when the object is far away, as is the case here, the image forms in front of the retina, and the eye cannot accommodate for bring the image here. It is then advisable to associate with this crystalline lens, which seems too convergent, a divergent lens. There is the symmetrical defect, I would say, the counterpart of myopia, which would be hyperopia. Those who have it have difficulty accommodating when the objects are close. They see well from a distance, and they cannot see well near. They see blurry. Why? Because the eye is then too little converge. The image forms behind the retina for nearby objects. It would then be advisable to associate it with, since it is too little convergent, a converging lens. Corrective glasses or a contact lens. That's it for this video. Thank you.